Hello everyone and welcome to another problem solving session on Special Maths Academy. And in today's video, we are going to cover the sixth problem from the Pan-African Mathematics Olympiad 2021. So the question is displayed on the screen, and on the bottom left is the construction to the problem. The two circles they asked us to prove are tangent are the circles in dotted red, and as you can see, they appear tangent, and one will vary some points. They also still appear tangents. So it seems our construction is behind the question. But we're going to then solve this question in a Olympiad way. So get back to that now. Okay, so in this question, how we are going to approach this question, we're going to use one popular lemma to solve this problem. So the lemma basically says two triangles or two circumcircles rather are tangent at a point. So these two circumcircles are tangent at this point if and only if from this point, let's say you draw straight rays that intersect the two circles at distinct points. So you can somehow show that these two lines here are parallel. These two lines are parallel. Let's call this point T, because one AB. Let's call this CD. AB is parallel to CD if and only if circumcircles of triangle TAB and triangle TCD are tangent at T. So these two lines, these two chords are parallel if and only if the two circles are tangent at that point T. So I'm going to prove only one part of this lemma. So the lemma I'm going to prove is when the two circles are tangent at that point T. So if that is the case, you can just then introduce the tangent at that point. And because both circles are tangent at that point, and this tangent line has to actually be tangent to both of those two circles at that point. So you can then use circle theorem. So by angle called tangent chord theorem, get that this angle theta is going to be called this angle here theta. And similarly to this bigger circle, get that this angle theta is also going to be called this angle theta. And by definition, if these two angles are equal, it means that they are corresponding, so they are parallel lines. So that is the part you can prove. The other part you use phantom points, but it's very similar to this. I'll just leave it to the viewers to do that. But actually, that is not the part where the part that I leave to the viewer is actually the part that we need to solve this question. But because two of them are equivalent, we just we can try to probably use the converse to see if we can get the converse. If the converse is true, then this is also true. And what the question asks us to prove is also true. So we're now going to go back to the question. This lemma is what is going to help us solve this question. So now that we're back to our question, what can we do? We just have to start introducing some lines to chase some angles. So first of all, this point S here, you can draw these lines here. Let me use a different color. From this point A, we can draw this line here, S, A, and draw this. Okay. Now, in order for us to apply this lemma to our question, the lemma I just showed here into our question, we are suspecting that the two circles are to be tangents, then an S is common both of them. Then we are suspecting that the point of tangent should be S, as the diagram implies. So if we can, to apply that lemma, we need to extend this line here, extend the ray to meet the bigger circle. Let's say maybe D prime. Let's call this A prime. So somehow, if we can show that this line, we can show that required to prove. If we can show that A prime D prime is parallel to AD, then by the converse of the lemma, to mean that these two circles are tangent at point S. We have broken our question out to shown that these two lines are parallel, A prime, D prime, and AD. So how can we do that now? Let's do a little bit of angle chasing. So now, because the quadrilateral AOSB is cyclic, let's call this angle theta. So it means that this angle is also theta. And similarly, these two lines are straight lines. So this is an alternate angle. This is also going to be theta. And because the 4 points ODCS is also cyclic, this is also going to be theta. Now we have in this bigger triangle, like this arc A prime B subtends angle theta on the bigger circle, and this arc also B prime C subtends the same angle theta on the bigger circle. So I'm actually going to show us another lemma now. If we have that, we have a circle, I have that, let's say an arc. Sorry, I'm using free-hand to draw this. So let's say if this arc now, let's call this ABCD. So this is cyclic quadrilateral. Let's say if this arc subtends angle theta, and this other arc BC still subtends angle theta. I know the configuration is it's a bit different. Like here the two lines not intersect, but here the lines intersected. But it's still the same idea. If this two angles subtend angle theta on the circumference of the circle, then by the extended law of science, or if these two angles subtend angle theta on the circumference of the circle, then to imply that the two chords that join the endpoints of those arcs are going to be equal. So you can do that easily by connecting to the center and do a lot of things. But I'll leave that also to the viewer. So if these two angles subtend the same angle on the circumference of the circle, it means that the chords that join the endpoints of those arcs are also equal. Now, if these two chords are to be equal, we can get something interesting also. So let's do a little bit of angle tracing. So these two chords are equal. So it means that this angle is equal to this angle, and also from here, we'll get that this angle here is equal to theta, because it's a cyclic quadrilateral, and this angle here is also going to be equal to theta, because it's a cyclic quadrilateral. So we have that this angle is theta, this angle is theta. So is actually a Z angle. So to imply that AB is parallel to CD. So from getting that two arcs form the same angle on circumference of the circle, we get that it implies that when you some pairs of chords are parallel. So this basically just means that if you have two equal chords on a circle, a lot of ways you can say this. You can say, like, if you have two equal chords on a circle, and when you connect the other two chords that are not joined, then those two chords must be parallel. If you have two equal chords in a circle, let's say this chord is equal to this chord, and it implies that these two other not necessarily equal chords must be parallel. So I'll just leave that to the viewer. Also, we can, but based on the configuration, sometimes the chords intersect, sometimes they don't intersect, but we can always use directed angle to finish that up. But if I don't only one case, it's still good enough. So we just have to keep this at the back of our mind. If we have two equal chords on a circle, just know that parallel lines are hidden along that circle. When we apply all these things I just said now, if these two angles are equal, it means that these chords subtend the same angle on a bigger circle. So it means that this line here, as I said, it means that this line here, this chord here, A prime, B, is going to be equal to this other chord here, B prime C. So they are segments, so we'll have to include this. So then, because these two are equal, this is what I said. It means that these other two lines are parallel. So it implies that A prime, D prime is parallel to BC. So we don't have to put segments here because it's not what we're talking about. So it means that these two lines are parallel. But remember, the question says that ABCD is a trapezoid. So BC in turn is parallel to AD. So we can then combine the first and the last one to get that A prime, D prime is parallel to AD. And this was what was required. We broke our question down. So remember how that proving this implies our question. So we have now proven what implied our question. So from here, we're done with our question. So the major idea was just the lemma, the first lemma, and this other lemma about equal chords, equal arcs, implying equal chords, which implies some parallel lines hidden. along the place. There are a lot of ways of solving this question. We may have also tried to introduce a tangent line. Okay, let's say you can just say draw a tangent line to one of the circles at this point. Then somehow prove that tangent line is equals to still tangent to the second circle, that we didn't define the tangent line to be equal. So there are a lot of ways of solving this question. You can just indicate in the comment section if you solve this question in some other ways that I didn't. Now I always try to respond. So this is all we have for today. Today was a short one, and I'll see you some other time. So thanks for joining us.